Titillinn Introducing the Electrical Power System Laboratory, eða EPS-Lab í HÍ. Gjörðu svo vel. Okay. Oh, do you...
I can connect to this port maybe.
Can I?
Thank you.
I will show you when you have 10 minutes and 5 minutes and 1 minute left.
That's good. Thank you. So thank you very much. Thank you for inviting me to this very prestigious event to introduce this new electrical power system laboratory to all of you. So I'm very grateful for all my colleagues, all my faculty members, especially my faculty members in electrical and computer engineering department at the University of Iceland. So they are giving me a lot of help for organizing this event and inviting me to this event. So I'm going to introduce this laboratory and the research work, the research background, and why we want to establish electrical power system laboratory, and what are the research opportunities and the industrial collaboration opportunities we can provide for other partners, and also for the industries, and also for the education opportunities for the students. So a little bit about myself. I'm Zhao Yuan, so I just recently got my joint PhD degree from KTH in Sweden, and it's a joint PhD program funded by the European Commission. So I got the opportunity to visit other two universities in Comillas in Spain and the Delft University of Technology in Netherlands. So backwards, I got my double master degree in electrical engineering and renewable energy from Huazhong University of Science and Technology in China, and also Paris Tech in France. I got my first bachelor degree in electrical engineering in Hebei University of Technology in China. I do have some work experiences in some industries and also academia institutes. So before I joined as an assistant professor in the University of Iceland, I worked as a scientist in Swiss Federal Institute of Technology in Lausanne in Switzerland for 2 years. Backwards, I also worked as a mathematical optimization advisor in Sweden, in KSE in energy, for several months as a part-time job. So the research work, so what we are doing in the electrical power system laboratory here. So we are doing many interesting, promising, and research, as well as we are developing many important and I believe, very vital technologies to improve the security, the economic efficiency, and also stability of the power system. So the first topic we have done, and we are also doing now, is about battery energy storage system. So we are developing and the real-time control system to provide voltage support and frequency support for the local grid. So this control system, I will give you more details later in the next slide, can reach a world record of response to the fast response to the local power grid situations within 100 milliseconds, which is a world record time of response duration. So the next topic is about convex optimum power flow. So optimum power flow, I will denote it as OPF. So this OPF model, this software module, it is the fundamental operational software module for every control room of the power system operators around the world. So it is useful for the economic dispatch, for operating your grid within an optimal level. For example, if you want to make many decisions in operating the power system, like how much power each generator in your power system will generate, at the same time, you should satisfy all the voltage, current, all the physical laws of the power network, and also your operational constraints, like the power limits and the lower limits for the voltage levels, for the frequencies. So you need to use this model. Basically, you need to solve the model to give you the optimal decisions. So the second topic is about the techniques and decomposition algorithms. So these are the solution methods in order to solve this, to solve the economic dispatch, to solve the OPF model, in order to improve the solution efficiency. So the next topic is about electricity market issue. So we are proposing to implement the nodal pricing scheme from transmission network to distribution network. So in this scheme, you can clear a price for different locations in your distribution network, which makes it possible to activate the flexibilities from each location of your network. Next topic is about renewable energy, which is about wind power integration. We are using voltage source converter based multi-terminal DC system and many flexible AC transmission devices to make sure that the uncertainty wind power generation can be dealt with, to make sure that the power system can be operated in a secure way, even though you have a 100% of wind power integration. So the next topic is about the supergrid coordination for ultra large-scale multinational power grid. So this is the real-time control system that we have developed, and it's running now for 24 hours each day for at the EPFL campus now. This real-time control system is based on advanced mathematical derivation of the actual operational and security constraints of the whole system. So this system is already connected to the local city distribution network. And we can prove that using the techniques that we are developing, we can guarantee the response time of this control system to the grid frequency and voltage situations within 100 milliseconds, which is a world record for the response time. So this is the battery topic. The next topic is about this OPF. So why we want a convex OPF? If you check the left graph, it is the OPF model of the original network, which is a non-convex model. And it's very, very hard to find the global optimal solution from this non-convex model. But by using some mathematical techniques, we can reformulate this non-convex model to a convex model, which is shown in the red figure. So what you can see is from this red figure, the convex model is very easy to find the global optimal solution, which means you can gain you can gain more economic efficiency, you can reduce your cost of generation, you can improve your voltage profile in a better way. We investigate this model in a very rigorous way, not only by case studies, not only by numerical studies, which means we can rigorously prove the properties, the optimalities of our models by mathematical proofs. So we have also published many papers based on these results. The next topic is about the integration of renewable energy. So the major challenge we want to solve in integrate a large amount of wind power is the uncertainty. So we all know that the wind power generation is intermittent, which means at one moment you can have like hundreds of megawatts generation from many wind farms. But for the next minute, it's very possible that you can have zero generation, depends on the weather situation. So how to deal with this large amount of uncertainties, especially when you have hundreds of wind farms with thousands of wind turbines together, integrated to your power network. And at the same time, you need to satisfy the demands from the energy consumers. So what we do with this uncertainty is that we use this stochastic programming approach to decompose the uncertainty scenarios from wind power generation to different sub-programs. And we propose a coordination program, a coordination mechanism to coordinate the solution process of this stochastic programming problem to make sure that the final solution is still global optimal for the original problem. So the advantage is that if you directly solve this wind power dispatch problem directly, you don't have sufficient computational power to solve it. You don't have sufficient RAM capacity in your computer to solve it. So if you decompose it to small scale problems, you can solve it in an iterative way. And you don't need to invest to more computational power, computational resources to solve this problem. So we test this program, and it is proved to solve a wind power scenario up to 10,000 scenarios. So next topic is about supergrid coordination. So I plot the topology of the European continent power grid. It includes the high voltage transmission lines for all the European continent countries, including France, Italy, Germany, Greece, Netherlands, and Belgium. So we all know that the European continent power grid is interconnected. And we do have coordination rules or some coordination codes to make sure that the interconnections, the interconnectors, the interconnected transmission lines, the power flows over these transmission lines always satisfy the security constraints. But the problem is that when you make sure that the constraints, the security constraints is satisfied, it's hard to make sure that the final power flows are optimal from a system level. So what we do is that we propose a concept which is called the Power Synergy Hub as a coordination center to coordinate the power flows of the interconnection transmission lines for multiple nations. So we used the power grid data for the whole European continental power grid for over thousands of transmission lines and generators and buses and also nodes. So and solve this model and find out that we can reach finally a global optimal solution. So the final topic is about distribution network pricing. We know that the price for the electricity is fixed for some countries for some time, but the problem is the price actually plays a very central role in market economy to make sure that both production and the consumption are efficient. So in operating the electrical power system, we want to make sure to apply the basic principles from economic theory to make sure the power system operations is not only secure, but also economical efficient. So what we do is that we implement some market mechanisms for both energy producers and energy consumers. And this market mechanism is called nodal pricing in transmission network. But in distribution network, this nodal pricing scheme is not implemented. So what we propose is we extend this nodal pricing scheme from transmission network to distribution network to make sure that the energy production and consumption are efficient, not only in transmission network, but also in distribution network. But in order to implement this nodal pricing scheme in distribution network, we have many technical challenges to overcome. So the first challenge is about computation. You need to use a very different model for distribution network to compute the prices. And the coordination challenge to coordinate the transmission system and the distribution system together. So the next challenge is about real-time pricing, which means you need to make the price not only different for each location, but also different for different hours. It means you can reflect the actual value of the energy, the electricity, for different time and for different locations. In this way, you can reduce the investment for network reinforcement. You can reduce your investment for not only distribution network investment, but also for transmission network. So you can check the prices that we have calculated in the third graph in the right hand. You can see different places and different locations. The prices are different. And whenever there are congestions in the network, you can see that the consumers who cause these congestions will face a higher electricity price, which gives them a very high incentive to reduce their energy consumption. At the same time, it can activate the generations, the producers to produce more, to release the congestions. Thank you very much.
So the time is up. Einhverjar spurningar sem vil kasta, en það hérna, yeah, this, we only have 20 minutes, sorry.
Okay.
But það einhverjar spurningar, may ég skjóta einni? Yes.
The pricing that you were talking about last time, because people typically make, I guess, contracts. Is this real-time pricing that will just be dynamically changed with the load?
Can you repeat the question for the mic?
The question is about the real-time pricing, the price differences for different hours, right? So the things we can provide flexible contracts from the retailer side to consumers. So you can choose from a series of different contracts you think is most economic for you. So in this way, you can, for the consumers, you don't need to face the risk directly from the wholesale electricity market. You can choose a fixed price contract. You can also choose a dynamic price contract. Which way you prefer, it depends on your own consumption pattern. So the only motivation or the only goal that we want to implement a more flexible contracts scheme for energy consumers is because in this way, we give more flexibilities for the demand side. And these flexibilities are very important to make sure that the whole electricity market is a dynamic, efficient market. So this is the major motivation, and there are more and more penetrations from the distributed energy resources like electrical vehicles, like batteries, PV panels on your rooftop, and small-scale heat pumps. All these distributed energy resources, they actually can provide much more flexibilities that the users can imagine. So the only thing is that they lack, they don't have the tools, they don't have the economic incentives, they don't have the proper ways to participate in the market, to make a profit. So I think this is very important why we want to implement this nodal pricing scheme in distribution network. So I would say it's a very important maybe the next step for the future power grid in Iceland also. Even though we don't have a market now, but I strongly believe that in the future, we will have a more efficient market also. Thank you.
Thank you. That's very
Thank you.